How's it going? We're going to talk more about ordinary differential equations. By the end of this, hopefully you can understand better that if you have an expression for the derivative of a given parameter or variable, that you'd be able to estimate that variation of the parameter over time for non-steady state scenarios, which can be pretty common. And usually you can specify the derivative from a mass balance or sometimes an intuitive understanding of relationships. But here we're first going to look at predator and prey, the interplay between those two. So here's the change in the number of prey, like perhaps a rabbit, and here is the predator, perhaps like a cougar. So you can see that the more prey you have, it's more likely that this slope or the number will increase as you have more and more individuals, and then it decreases the number of prey based on the product of prey and predators by a factor. Similarly with the predator, the increasing number of predators, the less likely, or there's a negative relationship with the number of predators in that change of the predator account, and that it can increase depending on how much prey there are. So we're just going to solve this with Euler's relationship, and we're going to specify some parameters for A, B, and C and D as I've defined here, and then also a step size, we learned that last time, and a maximum time. And then we set up our arrays of zeros given the maximum time and the time step. And then we're just going to use Euler's method, where we have the derivatives right here, d prey and d predator, and our prey counts just increase per our Euler prey equals prey from the previous time step plus d prey times dt. And you assign those right there from the previous values. And you can plot that, so you can see that the predator count rises because the prey count is high, and then the prey falls off, and it eventually comes back, and it's a little bit of a cyclatory or oscillatory pattern that also you could expect to happen in nature. The second example is some Lorenz, the Lorenz equations that were developed by Edward in 1963, and it kind of relates the temperature variation, convection rate, and vertical temperature variation for weather patterns. But the sigma, rho, and beta are constants, and then x, y, and z have those convection rate, horizontal temperature, and vertical temperature in this case. And we set up our Lorenz derivatives and then set initial conditions in our time step and our max time span here. And then we use, again, Euler's method. And you can plot that in three-dimensional x, y, and z. And it has kind of a cool pattern to it. And you can relate that to natural phenomena. The third example here, quickly, is I have a terrarium, and I made this terrarium. But the first time I made it, as you can see, I put some plants in there and soil and the rocks and water and sealed it off, and all the plants died. So I was investigating why that happened, and so I didn't have any plants. I took all the plants out and was just looking at CO2 concentrations, and there's quite a bit of CO2 that is produced at a rate inside that terrarium from the breakdown of organic matter by the bacteria in the soil. And so if I specified a rate of change of the CO2 inside the terrarium as a constant, so it's constantly changing, or it's a zero order kind of relationship, then you can also solve that. Here I've done it analytically, and you can integrate that. You just get a linear relationship. And then I went and measured the CO2 concentration, again without any plants. And here's some data. I've got it posted here on my GitHub site. I'll read that data into pandas data frame. And here is a plot of the time and the CO2 concentration. So you can see that it initially rises quickly and then kind of tails off or bends as the CO2 concentration increases. My initial estimate, and I just shifted this around to line up here by changing the slope and intercept values, but it's not necessarily linear the entire time. So what's a better model? Perhaps the CO2 concentration increasing affects the rate that the bacteria produce that CO2, and that appears to be what happens. And so I've added in here a term that reduces the rate of production of CO2 based on the concentration of that CO2. And we'll just solve this analytically with SymPy. It's a fairly straightforward integral, but there it is. And I'm just going to make a function there, right there. And then all I've done here is guessed repeatedly a few parameters for my C1 and K1 and K2 to get somewhat close. And you can see that it gets somewhat close, much closer than our initial estimate. So it does appear to be affect the CO2 generation rate based on the CO2 amount present. And perhaps a better fit, I've got a mistake in my mark down here, but perhaps a better one is not necessarily CO2 to the first power, but maybe it's to the half a power, so it doesn't level off so quickly. But you could do that and see if it fits better. But as far as fitting and determining these constants K1 and K2 and C1 above, we'll talk about that next time in regression. God lives and loves us.